Hello, everybody, and welcome to the final week of Socratic Med's 15-week MCAT supplement course. My name is Chris. Today, we're going to be talking about sleep and consciousness. So this is the last week of the program. So this is actually going to be a pretty quick lecture. We're just going to talk about consciousness, then we'll talk about sleep and dreaming, and then we're just going to touch upon circadian rhythm really quickly. The good part about this stuff is it's not super high yield and it's pretty interesting. So this should be a pretty easy lecture for everyone to get through. So just to introduce the company, as I usually do, Socratic Med is a grassroots nonprofit that provides sensible solutions to students with disparate medical school opportunities. So if you are interested in learning more about the company, I put a bunch of our contact information down there. We do have an Instagram page, a YouTube page, our website. We're constantly developing it. We're updating it. We have a GroupMe, which is how we pretty much keep in touch with all of our students. And then at the very bottom, there's a link tree over there. It'll link you to a couple of the things that I've mentioned over here. And it will also link you to our one-on-one office hours that we do with the 4 tutors that we currently have at Socratic Med. And on a more personal note, my name is Chris. I graduated from Stony Brook University in 2019. I finished a pre-med track and I finished with a BS in applied math and statistics. I did take the MCAT in April of 2021 and I scored a 520, which was the 97th percentile for that test. And I did get a perfect score on the psych-soc section. So my tutoring specialties are biology, psychology, and sociology. And if you need help with any other sort of subjects, chem, physics, orgo, biochem, cars, any of that stuff, we have a bunch of tutors here. Each of us specialize in different things. So there's always someone here that can help you with any questions that you may have. Okay, so we're just going to dive right into it. The first half of this lecture is going to be based on just observing consciousness, really what it is, how we can make sense of it. So what is consciousness? The specifics of consciousness are not really completely understood. We're not super aware of what it is. It's sort of this black box thing where we could see the effects. We're not really sure the causes. We're not really too sure of the inner workings. But what we do know can be pretty useful, just to evaluate human behavior. So consciousness, basically the best way we can define it is that it's our self-awareness, our awareness of our environment. And obviously those levels of awareness are going to they're going to fluctuate throughout the day, throughout your lifetime, sometimes naturally, sometimes not naturally, and we'll get into that in a couple of minutes. Consciousness is affected by alertness and arousal. We can pretty much measure consciousness by the level of alertness and arousal. So when arousal is impaired or when it falls too low, the individual is going to experience a loss of consciousness. So sleep, for example, is a loss of consciousness, and that usually happens periodically and naturally, but it happens when our arousal falls to really low levels. So part of the brain that's responsible for controlling arousal is known as the reticular formation. So if you look at this diagram to the right over here, this is sort of just a cartoon diagram of where the reticular formation is, which is over here, kind of upper by the brainstem. So I'm sure, as you know, the older sort of more conserved structures in the brain are usually closer to the brainstem. So those usually those are usually structures that are involved in, breathing, balance, arousal, sexual functioning, those sort of basic primal survival needs that we have. Those are usually mediated by structures that are close to the brainstem. And as you move farther out, closer to the cerebrum, those sort of association areas and those areas of higher processing are the more evolutionarily recent structures that are sort of specific to more recent organisms like humans. So although consciousness is necessary for human survival, our bodies naturally experience periodic reductions and losses of consciousness. So during sleep, for example, we can experience a loss of consciousness that can be categorized into stages based on the brain activity recorded. So EEG, if you look at this picture to the left, it's called EEG. It's also known as, fully the name is electroencephalography. So by strapping these sort of electrodes to an individual's head, you can sort of record the brain, the wavelengths that are coming out of the brain. And we use the different types of waves that come out at different points in the night to categorize sleep into multiple stages. There are actually 4 stages of what we call NREM, non-rapid eye movement sleep. And then there's 1 stage of REM. And we're going to go through all of those right now. So the stages of sleep, you can look to the bottom. This is a graph that you'll sort of see pretty often when we're talking about sleep. It's just a way to show the progression of an individual on any given night, how they progress through the different stages of sleep. So if you look at the y-axis, we have awake, stage 1, 2, 3, and 4. And then when you go from left to right on that x-axis, you can see as this line gets deeper, this individual is moving through the different stages of sleep, and they periodically come back to that REM sleep, which we're going to talk about. And you can also see, notice now, which again, we'll talk about in a little bit, is that as the night goes on, the individual spends more time in REM than they do in NREM sleep, which is a common theme. It's common for most adults. Okay, so waking consciousness. In this state, an individual's level of alertness may vary. So we're talking about waking consciousness, which means throughout the day when we are awake, just your normal average human being when they are awake. So when there are different types of waves that your brain gives off. A couple that are given off in the waking state and a couple that are given off in the sleep state. And we can basically tell sort of the level of arousal and the level, sort of like how aroused or alert you are in terms of conscious level. So for example, your brain gives off alpha waves when you are in this sort of relaxed and sleepy state. So if you're laying in your bed, you're getting ready for bed and you sort of feel that calm come over you, you're sort of winding down from the day. You're not really processing a lot of information at the time. You're not really using any cognitive ability, so your brain is sort of drifting off to the autopilot, but you're still fully conscious, you're still fully aware of your surroundings and your environment. If you had an EEG on, then it would show alpha waves. So these alpha waves are sort of small waves, but again, they indicate a relaxed sleepy state that your brain gives off. So the other waking type of wave is called a beta wave. So these are higher frequency and lower amplitude than alpha waves, so they're smaller than alpha waves is the term that we would use. So those indicate a focused and alert state of consciousness. So if you look at alpha and beta waves, when you're looking at these waves, the general trend is that the smaller the waves are, so the more waves there are in a specific period, which we call the frequency, and the smaller the amplitude of the waves, that generally indicates a more aroused alert state. So I didn't write anything about gamma waves, but they are up here on the diagram, for example. So gamma waves, you can see the frequency is a lot higher than beta waves, and the amplitude is similar, it might be even a little bit smaller. But when you compare these really tiny waves to theta and delta waves, which we're going to talk about in a minute, you can see a marked difference between the two of them. So these smaller waves with these higher frequencies, they indicate that the individual is awake, is aware, and that they are, the smaller the waves get, like when we're getting toward these gamma waves, it's sort of problem solving, concentration, those sort of, those high cognitive processes. So that's, those small waves are indicative of that. So when an EEG shows a person transitioning from beta waves to alpha waves, it's an indication that they are preparing to enter sleep. So there have been, numerous sleep studies. They do sleep studies all the time. PSGs, they're called polysomnographies. That's the way that we can, measure EEGs, breathing, heart rate, a couple of things. So a sleep tech, for example, when they're looking at the EEG and they see the shift from beta waves, these smaller waves to alpha waves, it's an indication that the individual is about to fall asleep. Once the individual does fall asleep, we enter stage 1. So during stage 1, the brain switches over to what are called theta waves. So these are low to moderate amplitude and intermediate frequency. So we can look over here. So this is drowsiness, more so drowsiness switching into the first stage. When your brain is giving off theta waves, you're in a very, very light sleep. Your awareness of your environment is definitely reduced if your brain is giving off theta waves, because technically you are entering that first stage of stage 1 sleep. So the sleeping person is less responsive to stimuli than during waking consciousness. These earlier stages, as you get deeper into the stages of sleep, you become less and less responsive to stimuli of the external environment. So stage 1, you can think of it like a sort of light sleep. You're just starting to get into the motion. You're not as responsive to stimuli in the environment if you were awake, but you still are somewhat responsive compared to other stages of sleep. So in this stage, there are slow rolling eye movements, and there's also moderate striated muscle activity. So your muscles are still moving. They're not completely paralyzed right now. So as your brain activates, as those different areas of your brain are activated, your muscles will activate as well, to the corresponding brain areas. So after stage 1, normally, you'll drift off into stage 2. So as the body leaves that stage and enters stage 2, the type of wave emitted on the EEG is still theta waves. So we're not really switching to a different type of wave. However, the pattern does change a little bit. So 2 wave patterns is what we refer to them as. They begin to emerge in stage 2. So stage 1 is mostly we're switching over from alpha to theta waves, and it's a pretty consistent stream of theta waves that will come out of the EEG. And then if you're watching it for a little bit, at a certain point, you're going to start seeing these irregularities in the EEG. So there are 2 sort of irregularities known as K complexes and sleep spindles. They both last about a ½ second to 1.5 seconds. And when you start seeing these sort of these sort of patterns interspersed in that theta wave distribution, that's indicative that the individual is entering stage 2 sleep. So the 2 K complexes is the first one, and these occur as a single wave burst that is lower in frequency and higher in intensity than the surrounding theta waves. So these last about 0.5 seconds. So it's a single wave burst. It's basically just one long wave among all of the theta waves. That's known as a K complex. And these are really just random bursts of energy from the brain. They're not really super well understood, but it is one of the ways that we classify and differentiate stage 2 from stage 1. The other pattern that is evident in stage 2, those are called sleep spindles. So those are short bursts of multiple waves with high frequency and moderate intensity. These typically last 0.5 to 1.5 seconds. So in basically the same time period as K complexes, there are sleep spindles as well. And the sleep spindles are short multiple waves. So if we see a K complex, it's usually going to be a longer singular wave that's out of the ordinary in terms of that theta pattern that we've been seeing. Sleep spindles are the exact opposite. They're a bunch of short waves sort of stuck in the middle of those theta patterns. So you definitely see both of those during stage 2. And also during stage 2, there's no more eye movements. So those slow rolling eye movements from stage 1 are diminished. There's no eye movement during stage 2, but there's still muscle activity. So the brain is still, slightly active, and muscles are moving. And it's not, you're not punching and kicking usually in your sleep. It's more so, muscle twitches, slight activations here and there. And this stage brings the body to a state of relaxation associated with sleep. So once we start to get to stage 2 sleep, the body is really entering that deep relaxation. So you're even less responsive to external stimuli. There's a decrease in heart rate, a decrease in respiration, and a decrease in body temperature as well. Okay, so stage 3 and stage 4, I put both of these on the same slide because they're not too different from each other. And I think until pretty recently, probably like 10, 15 years ago, NREM was actually only divided into 3 stages, but recently stage 4 of NREM sleep has also been defined, and we'll go over that right now. So stage 3, the brain intersperses theta waves with delta waves. So the new wave that we're learning about on this slide are known as delta waves, and these are high amplitude and low frequency. So we call these slow waves. They're indicative of deep sleep. So stage 3 and stage 4 is also sometimes referred to as slow wave sleep, and that's because of the delta waves that are given off. So if you look at this delta wave, you can see these crests and peaks are so long. It's just a completely different kind of brainwave than, say, if you look at beta. So you look at these 2 EEGs, you know for a fact that these are 2 completely different waves. So these really, really long, large waves are called delta waves, and those are indicative of very deep sleep. So when you see these waves, there's not a lot the person can do to react to external stimuli. They're almost completely unreactive unless there is a huge, disruption in this person's sleep. So they're continuing to display no eye movement, and still they have moderate muscle movement. They're unresponsive to external stimuli. And so as the brain switches completely to producing delta waves, so remember in stage 3, it's delta waves and, interspersed with these theta waves. As the night continues on and we're getting closer to stage 4, delta waves become predominant, and eventually the brain stops producing theta waves and completely starts producing delta waves. So when that happens, the person is considered to have entered stage 4 sleep. Heart rate and digestion slow further, and at this point, growth hormone is secreted as well, which obviously lets us understand, and it points the direction to the fact that sleep is important in growth and development. And then we have REM sleep. REM, which is short for rapid eye movement, is most easily identified by the bursts of quick eye movement present. So if you see an individual sleeping, you probably very quickly, even without a trained eye or without any sort of knowledge of the topic, you would very quickly be able to see that they're in REM sleep because you could actually see their eyes moving through their eyelids. So the waves emitted during REM sleep closely resemble waking beta waves, which is very interesting because when we enter sleep, we're still sleeping. We are still unconscious and unresponsive to external stimuli. So we're going from that deep wave sleep, we're going from that long wave sleep, stage 3, stage 4, to REM sleep. So those super long waves, those turn into these REM waves that very, very similarly, they sort of mimic beta waves, these waking waves. So it's really interesting how brain activity during REM sleep, is almost identical to brain activity during daytime. So during the stage, there's virtually no muscle movement, which is different, remember, from the NREM stages, where we do have some muscle movement, although the brain activity resembles a conscious alert state. So for this reason, REM sleep is also referred to as paradoxical sleep, because it's a paradox. We're still sleeping. There is more brain activity in REM sleep than there is in any other stage of sleep, yet there is virtually no muscle movement. So we increase brain activity, but we decrease muscle movement completely. So that's why it's called paradoxical sleep. But scientists are now pretty much thinking that REM sleep is super important for cognitive and memory consolidation, and just for repairing of certain structures in the brain. And dreaming typically occurs during REM sleep just because there's so much brain activity. So it does occur during REM sleep, but there is growing evidence that most people can dream in NREM stages, like stage 3 and 4. So the chronology of sleep: throughout the night, your body will cycle through REM and non-REM stages 1 through 4. Each cycle lasts about 90 minutes. And when I say a cycle, it basically means going from NREM to REM and then out of NREM. Cycles don't necessarily have to go through all of the stages of NREM. It's basically just NREM to REM to NREM. So it's possible to jump stages of sleep instead of moving through them sequentially. A person can leave stage 2 to enter REM, for example. And we sort of saw this graphic before, but if you look towards the beginning of the night, this individual will enter stage 1, stage 2, stage 3, stage 4. Then they're climbing back up stage 3, stage 2, and then they jump from stage 2 all the way to REM. And then they sort of follow a similar trajectory on the second cycle. They go up to stage 2, go back down, go up to REM. But when you come over to the right later in the night, you can see that some of these stages are skipped. Over towards the end, we again go from stage 2 to REM. And the second half of the night, we're not even reaching stage 4. So it's not completely necessary, and a lot of times it doesn't happen, that you have to experience all of these NREM stages sequentially before you can get to REM. So it's possible to jump stages of sleep. We said that infants spend about 16 hours a day sleeping, and much of this is spent in REM. So generally as an organism ages, they need less sleep per night, and they also spend less amount of time in REM. So this is basically more evidence of the importance of REM in growth and development, because infants and organisms that are developing spend a larger fraction of their sleeping time in REM. Teens need about 9 to 10 hours a night of uninterrupted sleep. And by the time a person is in their 60s, they may only need 6 hours of sleep a night, for example. Average humans get about 6 to 8 hours of sleep. And the older you get, the smaller the fraction of time you spend in REM sleep a night it decreases. Okay, so that was pretty much all we really need to mention about sleep on the MCAT. Like I said, it's not a super high yield, but it's really interesting. And if there's anything that's unclear, please email me or please look it up yourself. There are so many resources out there that can answer some of your questions about any of this stuff. So we're going to talk a little bit about circadian rhythm again. Again, not super high yield, but it's really interesting. So all humans have a biological clock known as the circadian rhythm. Circadian rhythm runs on a 24-hour cycle with conscious alertness varying at certain points in the day. Because of modern lighting, a lot of people actually say that the circadian rhythm runs it's closer to a 25-hour cycle, just because of the invention of artificial lighting and electricity. It sometimes kind of messes up our circadian rhythm. So a lot of people now are saying that a 25-hour cycle is actually a little bit more accurate when describing the circadian rhythm. And it could also describe reasons why we feel so tired, in a world that has artificial light. So at night, heart rate, respiration, and body temperature all dip naturally as a part of our circadian rhythm. And an individual's energy levels increase during the morning. So we're waking up. We're going to increase our energy levels during the morning. We sort of dip in the afternoon. We hit this sort of relative low. That's usually when people take breaks from lunch. Europe, they take siestas, they take a couple of hour break, maybe a nap in the middle of the day, just because productivity and energy levels naturally dip in the afternoon. So you could take a quick nap, maybe have a cup of coffee. In America, we don't really take naps in the morning. We just work through. And then after that, usually your levels pop back up, circadian rhythm increases a little bit, and your energy and alertness levels, they remain elevated until nighttime before sleep, when we start to wind down for the rest of the night. Circadian rhythm can vary from person to person, and it's based on factors like age, exposure to light. So like I was talking, the artificial light, for example, is altering all of our circadian rhythms, and age affects it as well. So for example, a 60 or 70-year-old person is more likely to wake up at 5 a.m. and fall asleep at 7 p.m. compared to a teenager. They have more of a delayed rhythm, where they're probably going to get up at 11 a.m. noon, and they're probably not going to feel tired until 11 p.m. midnight. So circadian rhythm is not exact, it's not definite, and it definitely changes with the environment. Okay, so light and hormones, sort of the way that we regulate circadian rhythm. So exposure to light can increase alertness and suppress the urge to sleep. Light is really the major way that our circadian rhythm is dictated. And that's why people who are blind sometimes have problems with their circadian rhythm. They can sort of get out of funk because they don't have that ambient input with lighting. There's a condition called non-24, specifically with blind people, where the lack of that information coming in because of the light messes up their circadian rhythm. So we turn to different methods to sort of keep that circadian rhythm on track, be it medications, taking melatonin on a schedule, things like that try to get the circadian rhythm back on track without having to use external light. So normally, though, as light is detected in the retina, it activates a section of the hypothalamus, which is known as the suprachiasmatic nucleus, or the SCN. Definitely know the SCN, know that it's involved in circadian rhythm, because you may see that term on the MCAT, and it's always good to know what those super complicated brain words mean. So the SCN is responsible for coordinating physiological changes with the time of day. Basically, it just takes how much light is in the environment, and it tells us if we're sleepy or not. When nighttime falls, there's a decrease of ambient lighting. The SCN stimulates the pineal gland to release melatonin. I'm sure everybody has heard of melatonin, is familiar with the increase in popularity of melatonin supplements recently. But melatonin makes the body tired before sleep, and it remains elevated throughout the night. So at night, when light decreases, the pineal gland secretes melatonin, and it remains in your body, and this helps us sleep. So as light increases in the morning hours, melatonin levels are reduced, they are suppressed, the pineal gland stops producing it, and the SCN stimulates the release of cortisol, which is that stress hormone that we've learned about. It's produced by the adrenal glands. It's involved in your stress response, but it's also involved in the natural wake cycle. So in the morning, cortisol is released, and it's actually responsible for you waking up in the morning. So cortisol increase, melatonin decrease. The result is that we wake up. So interesting stuff, not too difficult conceptually, but it's a very good idea for you to know that. So this is the only review question that I have for this lecture. So read it over, take about 2 minutes, pause the video because I'll go over it in about 5 seconds. Okay, so which of the following is our most consistent signs of an individual falling deeper asleep? So the answer is C, 2 only, and we'll go over it. So 1 says a change from alpha waves to beta waves. So if we're falling deeper asleep, we just have to think about what alpha waves are and beta waves. So alpha waves are those relaxed waves. They're a little bit bigger than beta waves. They're the waves that come when we are feeling relaxed, when we're about to drift off into stage 1, whereas beta waves are, they're sort of congruent with active thinking. So if we're going from alpha to beta, we are not falling deeper asleep. We're actually increasing our cognitive arousal, and we're increasing our awareness. So 1 is not correct. 2, dozing off to enter stage 1 of NREM sleep. that would be correct, because when we doze off entering stage 1, we're switching sort of from alpha, those alpha waves to theta waves, and theta waves are indicative of stage 1 of entering NREM sleep. So 2 would be correct. 3, light suppresses the production of melatonin. If light is suppressing the production of melatonin, there's a good chance we are in early morning and the individual is actually coming out of sleep. So again, 3 would be incorrect. And 4, as night falls, the production of cortisol increases. Again, when night falls, the production of cortisol doesn't increase. It actually decreases, and then cortisol increases in the morning when light increases. So 4 would be incorrect as well. It's inconsistent and it's just incorrect. So the only correct answer out of all of those Roman numerals is number 2. So the only answer that is consistent with that would be C, 2 only. Okay, so dreams and sleep disorders, super quick section, and then we're going to wrap it up. 5 common types of sleep disorders. We have insomnia, sleep apnea, hypersomnia, narcolepsy, and parasomnia. We're going to discuss 1, 3, and 4. Hypersomnia, feeling exhausted after 8 or 10 hours of sleep. Parasomnia is abnormal or unusual behavior during sleep. Don't really think there's a need to expand on those much more than that. That's really all they are. And again, it's not super high yield. But dreaming and its theories. So we have our good friend Freud over there to the right. So dreaming is thought to primarily occur in REM sleep, although there is growing evidence that most people also dream in the NREM stages of sleep as well, specifically stage 2, 3, and 4. So according to Freud, a dream had manifest and latent content. So just like all of Freud's other theories, basically what it is that we have something that we're seeing directly, and then there is always some sort of underlying or symbolic meaning of this content. So he also thought this applied to dreams. He thought that basically when we look at a dream, when we look at the plot, we can analyze it and we can learn about ourselves. So the manifest content of a dream is the explicit plot. He believed that this content was symbolic of underlying concepts of our drives, our fantasies, and conflicts that we may experience in waking life. So he believed that the latent content is what the manifest content was symbolizing. So the latent content is the actual drive or the actual content. And this stuff comes out in dreams because it's difficult for us to express, or it's difficult for us to acknowledge during waking consciousness. So Freud believed that this was sort of the subconscious's way of letting out these sort of drives or these conflicts. It was a way for us to express it, subconsciously. There's really not any merit, to these theories. This theory, just along with like psychodynamic theory, a lot of it is, even today in universities, it's more so housed in the literature section than it really is the science section. So it's not super evidence-based stuff, but it does have important implications in literature, history, and I'm sure you're going to come across it. So Freud's theory on dreaming, like many of his other theories, as I said, have been surpassed by evidence-based and more likely theories. So dreaming is important, for memory consolidation and cognitive regeneration. Like we've been seeing, that sort of brain activation in REM sleep, and the fact that, babies have a lot of it and older adults don't have a lot of it. There's a lot of mounting evidence to support the activation synthesis theory and other theories, other evidence-based theories, utilitarian theories, basically. So some studies in rats have shown that brain activity during REM were associated with increased performance upon awakening with activities associated with the active brain area. So for example, if the activity were running, rats would be running in, their waking consciousness, they would fall asleep. If it was recorded on an EEG that the specific area of the brain, for example, that's associated with running, if that were active during REM sleep, the rat woke up and started doing that same exact activity, started running, there was evidence that it had actually improved the rat's performance for that specific brain area. So that's very interesting. That's, basically just evidence for activation synthesis. And the implications imply that that's true. And really all that theory is, it just suggests that dreams are the byproduct of random brain activation during REM. So basically, it's just a natural thing that your brain does when it's sleeping. That's the way it repairs itself. It sort of test runs everything when you're sleeping. Your muscles are paralyzed, so it's an easy, safe way for your brain to sort of go through the motions. And it just so happens that doing this it produces dreams. So your brain, your conscious mind sort of strings together this activation of different brain areas, and it sort of puts it together into one dream. So activation synthesis basically just says it's a random byproduct. Dreams aren't really the main event as it is in Freud's theory. They're just sort of a byproduct of our biological brain consolidating and doing what it's supposed to do. Again, yeah, and it's opposite of Freud's thought that dreams have inherent meaning. So activation synthesis theory is probably what you would see if dreaming comes up on the MCAT. And again, it's really simple. There's not really much else you need to know beyond that, really. And then sleep disorders really quickly. So the average adult human should spend about 6 to 8 hours per 24-hour period sleeping continuously. Obviously, this isn't always the case. The most common sleep disorder is insomnia. I'm sure a bunch of people watching this have experienced insomnia, or someone that experienced insomnia, and that's the persistent inability to fall and or stay asleep. So it has to be persistent. It's not just one bad night of sleep. It's a condition that is persistent, that's chronic, that is actively interfering with your daily life. So insomnia interferes with the REM and slow wave sleep, and it leads to daytime consequences like irritability, fatigue, drowsiness, specifically decreased cognitive ability, which can be dangerous if you're doing stuff like, operating a motor vehicle for a living or operating heavy machinery. If you're a surgeon and operating, so it's not something that's taken lightly. And there are a lot of these sleep disorders. They can bar you from doing certain professions. So inversely, narcolepsy is categorized by sudden periodic sleepiness during the day that usually lasts up to 5 minutes. And it's currently treatable with stimulants. Yeah, there's not much else to know about narcolepsy in terms of the MCAT. It's just sudden periodic sleepiness during the day. It's not normal. And it usually is treated with modest success. It's treated with stimulants. Sleep apnea is the other one of the more common ones. It's a condition in which people stop breathing during sleep. A lot of times people snore when it happens. They'll choke themselves and they'll wake up. Sometimes you can wake up a couple of hundred times in a night and people won't even remember it just because they fall back asleep immediately. But regardless of if you remember it or not, it very, very much interferes with the quality of sleep. And it has a bunch of direct effects on your health. So it's going to increase the individual's chance of developing other comorbidities, high blood pressure, and the incidence of sleep apnea is very closely associated with obesity. So sometimes it has to do with congenital defects, but a lot of times obesity is also a risk factor for sleep apnea. So if an individual is obese and they do have sleep apnea, they'll probably be prescribed like a PAP device. PAP is PAP, it stands for positive airway pressure. And it's just a way to make sure that the patient is getting airflow throughout the night. But that's sort of, like not a temporary fix, but that's sort of an immediate fix. But a more long-term fix usually is the individual would, be advised to lose weight, because a lot of times when an obese individual does lose weight, the sleep apnea tends to resolve. And that is all I have for today. I said it was going to be a quick one. If you guys have any questions, again, email me, christopherscagnelli1@gmail.com. I'd be more than happy to answer your questions. I can add you to the group me or help you guys out with anything else that you have. That pretty much concludes the MCAT supplement. So make sure you guys are studying hard. Make sure you're going back using the other videos for the 15-week course in conjunction with this 15-week MCAT supplement. And again, the 4 tutors are still here. We're still doing one-on-one office hours. We're all open for questions. So as you guys are studying for the test, if you think of any questions, if you want any advice, anything, please feel free to reach out to any of us. All right. Best of luck. Happy studying.